Hello everyone. So today we see the statistical mechanism. What is statistical mechanism? So the statistical mechanism is the bridge between the properties of individual atoms or molecule described by quantum mechanics and the macroscopic thermodynamic properties like delta G, delta H, T, delta S, like that. So the main goal of statistical mechanism is to describe macroscopic thermodynamic properties in terms of microscopic atomic and molecular properties. Okay. So properties of a system can be described at two levels. Okay. One, macroscopic thermodynamic description like pressure, volume, moles, CV, like that. So in microscopic description, specify the state of each molecules, use classical or quantum mechanics more than 10 power 23 variables and need to update them every minus 15 second and so. Okay. So microscopic description of system, okay, or macroscopic system. Okay. Either classical or quantum description is impractical. Okay. So statistical mechanics describes macroscopic mechanics in statistical terms, that is in terms of average or most probable terms. Okay. That is the main property of statistical mechanics is the average or most probable result is the um, that is the real state. Okay. So most of the system are in the most probable state. Okay. Probabilities of system in a state with a given energy. Okay, what is a functional form? Okay, for independent energy psi a and psi j, the joint probability should be the product. Okay, so always the probability is joint probability is the product of psi I and psi j. Okay, subject exponential form, the only in the exponential form adding two functions give the multiplication. Only in the exponential form, if you add two function you get a multiplication of function. Okay, so it suggests that the energies of adding you get the energy multiplied. Okay, so functions it is in the exponential form. Okay. Okay, so then we expect a high energy state to be less probable than a low energy state. Okay, so because it is higher energy. Okay, so the molecule being at the higher energy is less probable, because less probable means it is not frequently probable. Okay, so only when the temperature are high, then the higher energy states are probable. Okay, so using that relation, you can derive the probability formula. E is equal to minus psi I by T. Okay, so when the temperature is high, the higher energies are probable. Okay, so this is the mathematical form of the definition. Okay, C is a constant greater than 0. Okay, okay, or more conventionally, it directly proportional to psi I divided by KT. Okay, the Boltzmann probability distribution. The constant is nothing but 1 by K. Okay, so where K is nothing but R by Na. Okay, R is a gas constant, Na is a number of moles. Okay, see, Na is a constant. Okay, so okay, equal to 1.38 into 10 power minus 3 erg per Kelvin, or in you can write in a joules or like that. Okay, okay, for two states I and J with the energy psi I and psi j. Okay, the relative probability. Okay, so for Pi, energy equal to e power minus psi I divided by kT. Okay, and for Pj, e power minus ej divided by kT. Okay, so then e power minus psi I minus psi j divided by kT. Okay, so if you take the e power minus ej into above, it become positive ej. Okay, so then you can take the negative outside and you put I minus ej. Okay, okay, this is simple. I think you understand this. When the temperature is high means the probability become low. Okay, because e power something negative. Okay, so when the temperature is high means the below high means the whole number become very small. When the whole number become very small, e power minus mean the probability increases. Okay, when the temperature increases, the probability of the higher energy state increases. Okay, so we derived in a mathematical form. Okay, if you know the mathematics, you understand this. Okay, to get absolute probabilities, not just a relative. Okay, so this is relative. So if you want to absolute probability, you should sum all the probability. Okay, so summing all the probability for all the state must be equal to 1. Okay, so this is for probability. In probability, summing all the probability, you get always get 1. Okay, so that is the important properties of the probability. Okay, so summing all the probability, you get 1. Okay, that is summing all. Okay, summation of I means summing all the I. Okay, I is the different states. Okay, e power minus ii divided by kt, and then a is nothing but take below 1 by psi I e power minus ii by kt. Okay, um, so this is directly proportional. Okay, so the a is just a proportionality constant. Okay, so then you can put to the a, if you know the a, then put to the a equal to pa equal to a is nothing but 1 by psi I e power minus psi I divided by kt. Okay, so probability of being in ith state. Okay, this is the probability, most important problem. Okay, then for a whole system or assembly of molecules in a particular system state I specified by indicating the state of each and every molecule with the energy ei. So for a system, for a whole system with the energy ei, you can replace psi I with ei. Okay, psi I with ei for system. Partition function is for molecular partition function. This is for molecular partition. This is for canonical partition function. Okay, canonical partition function is nothing but for a system, whole system, for whole system with n volume, temperature. Okay, constant number of moles, constant volume, and constant temperature. So this is the canonical partition function for a whole system. Okay, not a single molecule. Okay, for a whole system. Okay, measure how probabilities are partitioned among different available states. They are unitless number. Okay, example, perfect atomic crystal lattice at 0 Kelvin, set ground state energy equal to 0. Okay, so the all other state energy is should be greater than kt. Okay, so because the energy is very low. Okay, so k into 0 means approximately 0. Okay, so it is approximately 0. So k into 0 also approximately 0. So all other states are higher energy. Okay, at 0 Kelvin, approximately 0 Kelvin, the other only ground state only possible. Okay, because the ground state energy is 0. Okay, then the partition function q equal to become 1. Okay, the only state the molecule can occupy is the ground state. Okay, so that is q equal to 1 means the only one function is available. Okay, then probability is nothing but e power minus e0 divided by kt divided by, this is summation of all the energy. Okay, e0 divided by kt minus e1 divided by kt, like that. So at a temperature 0 Kelvin, all the other energy becomes 0 because no molecule can go to that at a very low temperature. No molecule has the energy to go to the higher energy. Okay, so all the higher energy become 0. Then you can cancel above and below, you get 1. Okay, probability is 1. Okay, 1, and that ground state. Okay, so for example, mole of atoms in a gas phase at a room temperature could be treated quantum mechanically like particle in a box states, or classically continuum of state of different kinetic energy, or use lattice model, divide available volume into so there are different methods. The one method is you can treat with quantum mechanically or classically, or lattice model. Lattice model nothing but take the lattice. Okay, different lattice, uh, divide the volume, available volume into atomic volume. So if you take these atoms are present in lattice, like this is the lattice model. If you take the whole volume is 1 meter cube, the total volume 1 meter cube. So if you take, and the atoms are normally in the Armstrong range. Okay, so cubing this 1 Armstrong cube equal to 10 power minus 13 meter cube. Okay, so then each atom has 10 power 13 possible 30 possible locations. Molecular translational partition function is nothing but 10 power 30. Okay, so there are, so one molecules occupy volume 10 power minus 30. So the total volume available is 1 power. So v by V, small v. Okay, so the total volume is 1 meter cube, but the each molecule occupy only 10 power minus 30 cube, 10 power minus 30 meter cube. Okay, so then if you take the total volume is 1 meter cube, and each molecule occupy only 10 power minus 13 meter cube. Okay, so then you can cancel out meter cube and meter cube, you get 10 power 30, positive 30. Okay, so that is 10 power available translational partition function. Okay, because each atom has 10 power 13 possible location to be participated. Okay, okay. For a system n equal to 10 power 24 atoms, if you take number of atom is 10 power 24, how many microstates? So how many ways to assign the atoms to selected locations? Okay, so for each atom there are 10 power 13 states are available. So the total states available is 10 power 13, which is huge. Then the number of atoms available, this is when only 10 power 24. Okay, so there are means there are plenty of space available. Okay, so if the first atom occupies, there is no change like that. So 10 power 24 atoms are occupying the 10 power 13 possible state. Okay, so then there are 10 power 24. Okay, so multiplying these two, you get the translational q translation the whole power n. Okay, so just the power n. Okay, there are partition function now available is q translation whole power n. Okay, the n is nothing but the number of atoms, 10 power 24. Okay, because each atoms has, if you take box only 3. Okay, you take here 9. Okay, so now first atom occupies the one position, the second atom occupies the other position, the third atom occupies other position, like that. So there are the first atom has like here 9 probability. Okay, so it can occupy here or here or here, like that, any position. Okay, so it has 10 power 13 probability. If you take the second molecule, it has also 10 power 13 possible state. In the reality, the first position is occupied, means the second molecule cannot occupy the same position. But there are more space available. Okay, so 10 power 13 minus 1 is approximately equal to 10 power 13. Okay, like that, 10 power 13 minus 10 power 24 is also approximately equal to 10 power 13. Okay, so all atoms occupied, there are plenty of space available. Okay, so because it is huge number, if you minus 10 power 13 minus 10 power 24, you get to the 10 power 30. Okay, approximately 10 power 30. Okay, so that is the mathematics. Okay, okay, I think huge number of distinguishable state is less than if the particles are indistinguishable, have to divide by n factorial. Okay, so this is for distinguishable particle. For indistinguishable particle, you should divide by n factorial. Okay, like if you take a lattice like that. For distinguishable means each particle you can differentiate with. Okay, so a and b, like that, c. Okay, so this is different from bac. Okay, so you can differentiate the different possible state. Okay, but if you indistinguishable particle means like dot. Okay, so each dot is indistinguishable, so you should divide by the n factorial. Okay, because it is same as AB is same as so if you A distinguishable means AB is different from BA. Okay, different from BA, distinguishable mean. But if you indistinguishable mean, this is same. Okay, so the from distinguishable indistinguishable, the number of state is reduced. Okay, so you should differentiate with respect to n factorial. For AB means 2 factorial equal to 2, there are two possible state. For n molecules, n factorial. Okay, for 3 ABC means you can 3 factorial. There are 6 possible state, you can arrange the ABC. Okay, okay, so these are mathematics you should know. Okay, Stirling approximation. This is the n ln n factorial equal to n ln n minus n. Okay, so calculating n factorial for huge number is very difficult. Okay, so that's why you Stirling's made an approximation ln n factorial equal to n ln n minus n. Okay, so the another form is n factorial equal to e power minus n into n power n. Okay, then substitute and do the calculation, you get the answer. Okay, smaller but still huge. Okay, so smaller than the distinguishable but still huge. Okay, so probability for any one system state is incredibly small. The probability is partitioned among a huge number of states. Okay, example, polymer if you take an example, polymer configuration include protein folding, just 4 polymer units. Okay, if you take four polymer subunits favorable, here there is a favorable interaction like hydrogen bonding, like that. So the energy is minus psi interaction. So int means interaction. Okay, so the other's energy is equal to 0. Okay, because there is no interaction. Okay, so then this is degeneracy 1. The threes are same energy. Okay, so that is degeneracy. Degeneracy means same energy. Okay, okay, in this simple example, the configurational molecular partition function is just adding all the so this is for interaction energy, so this is for 0. So you can add all this into 3 into e powers. Okay, so nothing but e power 0 is 1. Okay, so e power e integration plus 3. Okay, so the last expression suggests writing the partition function as a sum over energy levels psi I instead of individual states. Okay, if you account for their degeneration. Okay, so instead of writing 3 times, you can just put to the degeneracy 3. Okay, so 3 into e power 0 by kt. Okay, so that is the degeneracy gi. Okay, the number of state with the same energy. So that is here 3 states are have the same energy. Okay, so you should know the difference between state and energy. Okay, so degeneracy. Okay, if you take this is the energy and this is the energy level. So first energy level, second energy level, third energy level, like that. The first energy level degeneracy is 0. So the second energy level, it gets two states. Okay, two states with the same energy level. Okay, if you take 3 state with the same energy, so these are state. Okay, these are level. So this is level, this is level, but these are state. Two states have the same energy, means degeneracy is 2. Okay, the 3 states are same energy, means degeneracy is 3. Okay, okay, so you should know these basics. Okay, this can be done for the canonical partition function too. If you account for the degeneracy psi I of system energy ei. Okay, so these are same for canonical energy. Just replace the psi I. Okay, this is the degeneracy, and replace energy with ei. Okay, all the thermodynamic function can be calculated from Q. If you know the Q, you can derive all the thermodynamic function. Okay, so like if you see the partition function, the partition function play a critical central role in the statistical mechanics. All the thermodynamics function can be calculated from them. Okay, start with the average system energy, that is internal energy. Okay, so that is the average energy of the system. Okay, that is the internal energy. So substitute beta equal to, if you take beta equal to 1 by kt. Okay, then the average internal energy or average system energy equal to sum of probability of all probability into all energy. Okay, so the pi is nothing but 1 by q into e power minus beta psi. Okay, pi equal to e power minus beta ei divided by q. Okay, that is the pi. Okay, substitute for pi, then use the following result, dou q divided by dou beta. Okay, if you differentiate q with respect to beta, q is nothing but summation of I into e power beta psi I. Okay, if you differentiate with respect to beta, you get summation of I e power minus beta I into, if you here beta, here beta. Okay, so if you differentiate, you get minus beta. Okay, minus psi I. Okay, minus ei. Okay, so then you get ei. So then substitute the answer, and Okay, so this is nothing but the dou ln q dou v. So this is for simplification, simple mathematics. Okay, so take 1 by you take the 1 by q equal into the this is nothing but dou ln q by dou beta is nothing but 1 by q into dou q by dou beta. Okay, so these are same. Okay, and dou ln q divided by dou dt. So these are also same. Okay, just for simplification. Okay, so by simplifying you get the answer internal energy. Okay, do the mathematics. Okay, lead to a natural connection with a equal to n t and v. Okay, if I do the mathematics it takes more time. Okay, that's why I skip the mathematics. Okay, a is nothing but u minus ds. Okay, so then substitute for s. Okay, so this is dA is nothing but minus p dv minus s dt and plus u mu dn for open system. Okay, so then from this you can derive this. Okay, so dA by dt at constant volume and n at constant volume and n this becomes 0 and you get minus s. Okay, you can substitute for minus s for this. Okay, so if you see these all you know the mathematics, you can derive a. Okay, constant of integration can be taken to be 0. Okay. This is the property of integration. Okay, if you know the mathematics, if you derive this. Okay, all the other state function like that, so like from entropy, pressure, chemical potential, enthalpy, g, all are derived from this ln q. If you know the q, then derive all these. Okay, entropy in terms of micro state probabilities and degeneracy. So if you divide the entropy divided by k and 1 by kt and take the u plus a, substitute for u and a, then this is our same. Okay, ea is nothing but, so this is our same. If you know, you can if you write it and these two are same. Okay, mathematically these two are same. Okay, so substitute these two and you get since probability a is equal to 1, we can multiply ln q into 1 is nothing changed. Okay, multiply with 1 is nothing changed. Okay, so you can multiply with this. Okay, so because sum of probability is equal to 1, so then you can take the summation. Okay, this is for simplification purpose. Okay, if you do the mathematics, the simplified. Okay, so then this is nothing but if the system is isolated, if the system is all the state have the same energy. If the system is isolated means then all the state have the same energy and the same probability. Okay, same probability p equal to 1 by psi. Then psi is the number of degenerate state. Okay, then you get to the Boltzmann law. So this is the important Boltzmann law. Okay, if the can understand entropy in terms of disorder or number of different available states, this microscopic picture of entropy is at the heart of statistical mechanics. Okay, so this is the heart of statistical mechanics. Okay, so even if system is not isolated, energy fluctuation are negligible for 10 power 24 atoms. Okay, so the energy fluctuation is very small. Okay, so can treat as if all the state have same energy, then we can equal probability, then you can use the Boltzmann law. Okay, so you can use the formula not only for isolated system, you can also use it for more molecules. 10 power 24 molecule means you can treat as all state have the same energy with equal probability, then you can use the Boltzmann formula S equal to k ln psi omega. Okay, so this is omega. Separation of partition function. When can we write the canonical partition function as a simple product of molecular partition function? Okay, so this is for distinguishable particle, this is for indistinguishable particle. So these hold the system micro state energy. Ei is the sum of independent molecular energy psi I denoted by the psi initial where ni psi ni where ni is represent various quantum numbers I. Okay, so this is, if you take ei is nothing but the summation of all the energy. Okay, so each state ni represents quantum number of for molecule I. Okay, Then sum over the system microstate is just the sum over all possible combination of molecular energy. Okay, so this is nothing but you can take E is nothing but En1 plus En2 like that. So if you in the E power addition means you can separate by multiplication. Okay, so this is the multiplication of our partition function for Q1, Q2, Qn equal to Q power n. Okay, for each molecule, the Q1 is for molecule 1, so molecule 2, so this is for whole. Okay, for a system. Okay, so the system contains n molecules. Okay, and for indistinguishable particle, then we can interchange the position. For indistinguishable particle, don't forget to divide by the n factorial. Okay, because indistinguishable particles, the states are very low. Okay, so if system energy equal to sum over independent molecular energy, canonical partition function equal to so if the system's energy is equal to the sum of independent molecular energy. Okay, the system so system is, if you take system, it has molecules 1 2 3 like that. Okay, 4 5. Okay, 1 2 3 4 5. Okay, so then if the system energy is equal to the sum of independent molecular energy, sum of 1 2 3 4 5 like that, then canonical partition function equal to the product of molecular partition function. Okay, the each molecule partition function. Canonical partition function is for the whole system. Okay, if you take the system 1 2 3 for each molecules, so this is for molecular partition function, this is for the whole system for canonical partition function. Okay, okay, so same operation for molecular partition. If molecular energy equal to sum of independent degrees of freedom, okay, sum of degrees of freedom energy, then the molecular partition function equal to product of degrees of freedom. Okay, because each molecular energy is, if you take a molecule, it has different energy: translational energy, rotational energy, vibrational energy. Like if you take a molecule like H2, so it has translational energy, rotational energy, vibrational energy, and electronic energy. So it is if you take a system of hydrogen. Okay, if you take many hydrogen, here this is hydrogen 1, then hydrogen 2. Okay, like that. For this is the whole, this is canonical partition function is for all system. Okay, product of molecular partition function. Each molecular partition function contains different degrees of freedom. Okay, like rotational, vibrational, like that. So molecular partition function Q also you can write as a product of degrees of freedom. Okay, like if you take a polymer in a solution, it has configurational psi energy and everything else others. Okay, so other energy. Okay, so then the Q is nothing but Q everything else into Q configurational energy. Okay, so we can calculate configuration and Q configuration even if other properties are hard to determine. Okay, so example, molecule with two distinct configuration has the same energy, psi configuration equal to 0. If you take the example, so this is like a polymer. Okay, if it has two configuration, it has same energy because there is no interaction. 2 has the same energy, psi configuration equal to 0. Okay, so calculate molecular and canonical partition function. Q and Q including translational. Okay, lattice model translation. Okay, n molecules in the gas phase, molecular volume is V and the total volume is capital V. Okay, big V. Okay, so all molecular position have equal energy. Okay, then the partition function is nothing but for translational V by V and for configuration also V by V. Okay, so then the molecular partition function Q equal to configurational partition function into translational partition function. Okay, Q is the partition function. Okay, so this is V by V into V by V, nothing but 2V by V. Okay, okay. Q translational is nothing but Q capital Q translation equal to small q translation whole power n divided by n factorial. And for configurational, you don't need to differentiate with respect to divide by n factorial, because each configuration is different. Okay, so you see this configuration is different from this configuration. Okay, so you don't need to divide by the n factorial. Okay, translational, you should divide. Okay, so for translational you should divide by the n factorial. For translation you cannot distinguish two translational. Okay, so q is nothing but q configurational into q translational. That is nothing but q configurational whole power n into q translational whole power n divided by n factorial. So do the mathematics. Could extend to include rotational, vibrational, and the other degrees of freedom. You can add other degrees of freedom also. Just multiply. Here only translational and configuration only added. If you want to add rotational, vibrational, and other, just multiply other partition function also. Okay. What is statistical thermodynamics? Okay, calculation of macroscopic thermodynamic result. Okay, like thermodynamics, you can also calculate in statistical thermodynamics. Okay, like entropically driven examples for free expansion of a gas. Okay, V1 gas to expand into a vacuum. Okay, the final volume is V2 and gas. Okay, so let's take a lattice model for ideal gas translation. Molecular volume is V, total volume is total V. All molecular positions have same energy. Okay, so all system microstate have equal energy. Okay, so the calculate entropy. Entropy is nothing but K ln omega. Okay, so in each state molecular degeneracy G is nothing but V by V. Okay, degeneracy is nothing but V by V. So system degeneracy is G power n divided by n factorial. Okay, so G is nothing but V by n, the whole power n divided by n factorial, from expansion of V1 to V2. Okay, so delta is nothing but K ln omega 2 minus K ln omega 1. Okay, so if you simplify, you get the relation, same relation. You know, if you remember this is the same as thermodynamics. N r ln V2 by V1, expansion against vacuum. Okay, so okay. Entropy change is positive, free energy change is negative as we expected. Okay. So ideal gas mixture. Okay, if you take Na moles at Va moles, Nb at Vb moles, so like that. If you take Na moles at Vb and Nb at Vb, okay, so then take the partition outside and assume the mixing. Okay, so assume same initial pressure and temperature for A and B. Okay, equal molecular volume and lattice cell size. Then the initial entropy is nothing but K ln omega A plus K ln omega B. Okay, so you can adding addition in ln is multiplication, become K ln say omega A omega B. Okay, so this is initial entropy. After mixing, count how many ways to distribute Na molecules of Na and Nb molecules of B among the V by V lattice sites. Okay, so as before, the number of way distribute N molecules among site is V by V site is V by V whole power N. Okay, so the final entropy is nothing but total volume V by V whole power N divided by the Na factorial divided by Nb factorial. So indistinguishability, for indistinguishable, you should divide by Na factorial and Nb factorial. Okay, delta is nothing but S2 minus S1. Okay, so simplify the result, you got the same result as the classical thermodynamics. Okay, like that for ideal liquid mixture. Okay, so in the liquids something different, because the liquid all the cells are occupied, because the all if you take a solvent, the all molecules are occupied in every site. Okay, so if you take a lattice model, the all sites are occupied. Okay, all sites occupied means the entropy of the initial solvent and this is solute are zero. Okay, after mixing the n molecules for n states, the first molecule has n choices. Okay, so then the second molecule only have n minus 1 states. Okay, so like that, if you put n into n minus 1 into n minus 2 into like that, that is nothing but n factorial. Okay, okay, so this is for delta S mixing is nothing but S mixing is nothing but K ln gamma mixing. That is nothing but n k ln n, okay, minus n k. Okay, so use the relation. This is nothing but k ln n factorial divided by na factorial divided by nb factorial. This is the total state divided by the na factorial and nb factorial. Okay. Then delta G mixing is X mixing minus SA and SV. So simplify it, you get the answer. Real liquids has additional states like positional disorder, molecular rotational, etc. But these occurs both in the pure and mixed liquid. So it is same in pure and mixed state. Before mixing also it is same. Okay, the disorder also same. The molecular rotational same. So the delta S mixing is does not change very much. Okay, so it is only dominated by the molecular position. Okay, what is combinatory? So if you take a simple example, mixing two molecules A of A and three molecules of E. If you take two molecules of A and three molecules of E, how many distinct configuration? Okay, so if you write all the possible ways of distinct configuration, you get 10. Okay, the 10 is nothing but 5 factorial divided by 2 factorial into 3 factorial. Okay, so this is how we put here. Okay, here we see, here you see mixing is n factorial divided by na factorial and nb factorial. N factorial is nothing but the total number of molecules. N is here total number of molecules. Here 5 total number of molecules. N factorial, Na factorial is 2 factorial, Nb factorial is 3 factorial. This is how the statistical mechanism work. Okay, you should know how. If you take two molecules and three molecules of B, after mixing, these are the possible state. Okay, only these possible state only, like only the two are in the same side, or two A and B and A B B, like that. Others A B B A B. Okay, others A B B B A. Okay, like that. Only 10 possible state. The 10, how the 10 comes from 5 factorial divided by 2 factorial, 3 factorial. That is how the n factorial divided by na factorial and nb factorial. Okay. Okay. These are mathematics you should understand. Okay. So energy and entropy changes. We saw one example earlier, 4 segment of polymer. Now the interaction energy is become, now we put the interaction energy 0 and the other energy just to put E interaction. Okay. So these three are same degeneracy 3 and this is 1. Okay. Same. Okay, now this is now redefined zero of energy as the ground state energy, zero energy as ground state energy, the other energy become interaction energy. Okay, okay, then degeneracy, to put the degeneracy 3 into, okay, then if this is become 1. Okay, e power 0 is 1. Okay, then 3 into E integration kt. Okay, for a solution of non-interacting polymer molecules, Q configuration nothing but Q of configuration whole power n, for n is the number of molecules. Okay, okay, we can determine A configuration and U configuration. Okay, if you know the Q configuration, you can derive the A configuration, U configuration. Okay, energy scale with n, molecules are not interacting with each other, so total energy is just a sum of individual molecular energy. Okay, okay, average energy per molecule. Okay, so if you take average energy is U configuration divided by n. Okay, so then we know E equal to psi I pi. Okay, so this is then substitute for pi e power minus beta psi I divided by q, then substitute the value, the same result, you get the same result. So you get S entropy also, you get the same result. Okay, so also scale with n. Okay, so sum over individual molecules, entropy contribution, average molecular configurational entropy is just scale with n. Okay, so just scale with n, you get the answer. Okay, here this equation become this. Okay, then you should know the high temperature limit. Okay, at high temperature beta become low, then k become then S configuration become k ln 4 as expected. Okay, ln 4, only 4 configuration. Okay, at high temperature the 4 configuration are possible. Okay, so then k ln omega, so the omega is 4. Okay, so entropy is nothing but k ln omega, so the omega is the possible state. Okay, so you get 4. Okay, so at a high temperature all 4 possible state are. So if you put beta is very low means this is become 1. Okay, this become 1, 1 plus 3 is 4. Okay, so this become cancelled. Okay, at a low temperature limit also this is become 0, low temperature limit this becomes 0, and you get to k ln 1. Okay, equal to 0. Okay. Okay, so this is chemical potential equal to dou A divided by dou N at constant temperature and volume. So these are mathematics you should know. Just mu configuration is nothing but differentiating A with respect to N. That is the mu configuration. So chemical potential is just A per molecules. A scales with N, so it's just A by N. Okay. Cv is nothing but dou U by dou T. Okay, so differentiating with respect to temperature, you get the answer. So this is like somewhat complicated, but you know the so scale with N, we can think configurational heat capacity for molecule, complicated function, but it is limits are understandable. So we should understand the limits. Okay, at a low temperature and high temperature. Okay, we see. So at a low temperature, at very low temperature, the KT become very close to 0. Okay, so then changing the temperature little bit, Cv is nothing but dou U divided by dou T, the change of internal energy when the temperature change. When the all molecules in the lowest state. Okay, so when the temperature are very low, the all molecules in the lowest state. Okay, then if KT increases infinitesimal amount, does not all the molecules are still in the lowest state. So if KT increases slightly bit, then now also all molecule become 0. Okay, so because the this energy level is not possible because the energy available at room temperature KT is very low. Okay, so the Cv also tends to 0 at temperature 0. Okay, the Cv configuration also tends to 0 at a temperature infinity. Okay, so Cv is nothing but dou U at it does not change in dou U divided by dou T, and that is Cv. Okay, when the temperature change, the du does not changing means Cv equal to 0. Okay, like that. At a high temperature, the KT is very high. Okay, so the all molecule occupy all the available state. So increasing the temperature little bit, KT become does not change the very much. Okay, does not change the internal energy. Does not change the internal energy means Cv equal to 0. Okay, at a low temperature midterm, Cv equal to 0 is common to all almost every degrees of freedom, since ultimately temperature is reached at which only the lowest state is occupied. Okay. Okay, so at a high temperature limit, Cv is characteristic of system. So at a high temperature, all are equal probable. Okay, so then also increasing the temperature does not change. Okay, the same in words. Okay, model system. Okay, if you're starting with quantum mechanical energy levels for molecular translational, rotational, and vibrational, solve for Q and all the thermodynamics for these degrees of freedom. The results are the fundamentals of molecular statistical mechanics. Okay, we will derive the results for a classical model that maps into quantum mechanical vibration. Okay, so you read this. Okay, so just if you take example, you take a polymer. So each interaction have the energy psi 0. Okay, so you minus psi 0. If you break this energy, you get to the energy higher. Okay, and if you break do bond, you get to psi energy, like that. So energy, each energy is non-degenerate energy. So if you break all the bond, you get to the energy of increases. So this is one configuration, this is one configuration, this is another configuration, this is another configuration. This is at energy psi 0, this is at energy 2 psi 0, because two interactions are cancelled out. The energy increased because interaction decrease the energy, breaking the interaction increase the energy. Okay, for a very long polymer, there is a large number of levels. Then we can extend the sum over state. Okay, in Q configuration to infinity, because at a higher energy are much bigger than the KT. Okay, anyway. So same calculation. Okay, so you get the same result. Okay. like that. You can all derive, if you know the Q, you derive all these. Okay. So particularly important are U configuration and CV at their high and low temperature. That is very important. U configuration and CV configuration at low temperature and high temperature limit. These are very important. Okay. At a low temperature limit, U configuration is 0, CV also 0. As we seen, at low temperature, all the molecules are in ground state, and slight increasing temperature leaves them there. Okay. So the system energy does not increase. At a high temperature limit, the U configuration become you put to the high temperature limit. Okay, so temperature become high means then if you hear the temperature high means, and the below high means the above value become so very negligible. Okay, so then you can put nkt. Okay, so if you do the mathematics, you know that. So then CV is nothing but nk. Okay. So the plus 1 minus 1 cancel out, and E0. So okay, so then you got the answer nkt. Okay, simplified. Okay, kt become if you take the kt above and cancel out E0, you get the nkt. Okay, so all are mathematics. If you take time and solve, you should understand this. The conclusion is very important. Okay, once the kt exceeds the temperature energy spacing, then further increasing temperature increases the occupation of higher levels. Okay, but the amount of energy increase with the temperature does not change any further. Okay, so U configuration directly proportional to temperature, but the CV is independent in the higher temperature limit. Because you see the U configuration nothing but nkt, it directly proportional to temperature, but CV is independent of temperature. Okay, because we already see, so at a higher temperature the CV is does not change very much. Okay, independent of temperature. Entropy and probability distribution. At a low temperature limit, S configuration equal to 0. K ln configuration, since only the ground state is occupied. Okay. At a high temperature limit, temperature tends to infinity means put to the temperature, you get the answer like this: K ln kt divided by psi whole power n. Okay. Note high temperature limit for Q and Q equal to 1. Okay, and the Q configurational equal to kt by psi, and at a temperature tends to 0 means it is 1. Okay, when temperature becomes infinity means kt by psi. For Q configurational, kt by psi naught whole power n. Okay, Q is a measure of how many states the molecule has thermal access. Okay, for kt is greater than psi 0, it's just a ratio of kt by psi 0. Okay, if kt is equal to 10 psi 0, then the molecule have thermal access to 10 states. Okay, like that. So Boltzmann distribution gives the probability of each state. Okay, so this is the probability molecular energy psi I. Okay, so the probability of higher energy is very low, probability of lower energy is higher. Okay, most likely molecular energy psi is 0 for non-degenerate level. Wide range of molecular energy may be occupied. Average molecular energy equal to greater than 0. System energy is nothing but n into psi. Okay, it is also greater than 0. Individual molecular energy vary widely. Okay, but system energy does not change. Okay, individual molecular energy can change very much, but the whole system is does not change very much. Okay, so like if you one molecule has very high energy, but the other but the whole, if you take the whole system, it does not affect very much. Okay, so how come recall Q equal to nothing but e power minus ei divided by kt, that is nothing but omega ei e power minus ei divided by kt. Okay, system energy. Also recall probability is nothing but e power minus ei divided by kt divided by summation of e power minus ei divided by kt. Probability of for system energy ei, probability of ei equal to degeneracy and e power minus ei divided by kt divided by summation of I e power minus ei divided by kt. Measurement of macroscopic system always yield the same result. Okay, probabilities for that system energy. Okay. Okay, system degeneracy increases sharply as energy increases. Example for 0 1. Okay, for energy increases the system degeneracy also increases. Okay, this weights probabilities in favor of higher system energy. Boltzmann factor decreases as system energy increases. The weights probability in favor of lower system energy. Average is the balance between these factors. Okay, probability is very sharply peaked. Okay. How much does the system energy fluctuate? If molecular average energy is high, molecular standard deviation equal to sigma approximately equal to psi, then system energy equal to n into molecular average energy n into psi. Okay, system standard deviation is nothing but root of n into sigma or approximately equal to root of n into e. Okay, relative system energy variation is nothing but system standard deviation divided by the system energy. Okay, then you got 10 power minus 12. Okay, so fluctuations are immeasurably small for a macroscopic system. 10 power minus 12 is very small. Okay, so for a small macroscopic system, the fluctuations are very small. Okay, relative system energy, so the fluctuation is very small. Okay, so system entropy S equal nothing but minus k into summation of pi ln pi for system at constant temperature. But we can approximate S equal to k ln omega, where omega e is the degeneracy of most probable level. This is okay because the range of system energy is very small. So this is the for system entropy, this is for formula. Okay, for we can approximate, this is for approximation because if you take the system energy, most system are in the most probable state. Okay, the other system are very low. If you take this is the most probable system, most system are come into the most probable state, the other is very low. Okay, so you can approximate into k ln omega. Okay, vibrational partition function and thermodynamics. The double stranded polymer model used here gives the same energy as quantum mechanical vibrational modes of molecules and materials. Classically, vibrational equal to half me square plus kinetic energy is nothing but energy is E equal to half me kinetic energy plus potential energy. Kinetic energy is half me square, potential energy is half kx square. The k is nothing but the force constant, x is the displacement. Okay, then the natural resonance frequency mu 0 equal to 1 by 2 pi root k by m. Okay, vibrational amplitude energy and can take any value continuously. Okay, quantum mechanical vibrational states are non-degenerate spaced by equal amount. Spacing is h mu naught. This is from quantum mechanics. Mu naught is nothing but 1 by 2 pi root k by m. Okay, so h is the Planck constant. We already done this problem. We can define the zero of vibrational energy as the lowest vibrational energy level, and we get to the identical result. Okay, so if you do the mathematics, you get the same result. Okay, important for molecular and material vibrational. So at a low temperature limit, mu vibrational equal to 0. With 0 as usually defined, Cv also equal to 0. Okay, at high temperature limit, U internal vibration equal to nkt and Cv equal to nk. So molecular vibrational frequency usually in the range of 1000 to 3000 centimeter inverse. Kt at 300 Kelvin is 200 centimeter inverse. Okay, K is Boltzmann constant, T is temperature. If you multiply these two value, you get a 200 centimeter inverse. So it is very low. Okay, so most of the because the molecular vibration you do for a molecular vibration, if you take a molecule vibrate, it need very much energy. That much energy is not available in the room temperature. Okay, so most of the molecule in the ground vibrational state. Okay, so that is at a lower vibrational state. So crystal lattice vibrational frequency is approximately 30 centimeter inverse. So, crystal vibrational frequency is approximately 30 centimeter inverse. So then this is very much higher than the 200 centimeter. This is very much low. Okay, so then the most crystal are in the high temperature limit, because the room temperature available energy is 200 centimeter inverse. So for the crystal vibration, we only need 30. Okay, means all the you can assume the high temperature limit. Okay, for n atoms in an for n atoms for n atoms if you take for n atom, an atomic crystal, there are 3n. Okay, the vibrational model. So at temperature T, Cv equal to 3 nk equal to nk is nothing but nr. Okay, so this was used to determine the molecular weights. Okay, so at lower temperature limit it become 0, at higher temperature limit it attains a constant value. Okay, that is nothing but 3nr. Okay, no one could explain why Cv equal to 0 at low temperature until Einstein suggests that in 1905 that if energy was quantized, not continuous, then the kT can be much lower than the first excited state. So kT can be much lower than the first excited. So then Cv tends to 0. This is the explanation provided by Einstein 1905. Okay, not possible if energy is continuous. Okay, not possible if energy is continuous. Okay, molecular translational, rotational and classical equipartition of energy, the results are derived in statistical mechanical, okay, course. Okay, so one key we see in the later. Okay, so one key result is for each degrees of freedom, 3 translational, 2 or 3 rotational. Okay, at high temperature limit energy is nothing but half kT and heat capacity nothing but half k. Okay, so translational it is into 3. Okay, into 3 by 2 kT. For rotational, for linear only 2 rotational are available, so into 2. For non-linear 3 rotational over 3 by 2 kT. For vibrational, kT for vibrational mode. This is the classical equipartition of energy. Okay, why does it comes about? Each degrees of freedom has kinetic energy given classically by half me square. If you take half I omega square for rotational, here I is the amount of energy, omega is the angular velocity. Vibrational degrees of freedom, that is kinetic energy equal to half me square and potential energy equal to half x square. All these squared energy terms can be written in terms of ay square. Okay, if you take if you see all the kinetic energy, potential energy and for angular velocity also the I omega square, these are all a y square, like the half m, this is constant, half is a constant, m is also constant. This you take a and y v square, yeah, or omega square v, like that, and take the y square, it is in the y square form. Okay, then you can use the average molecular energy for any of these degrees of freedom is given by the formula psi I equal to psi I e power minus psi I by kt divided by e power I to infinity e power psi I kt. But if the levels are spaced close together relative to kt, then we can convert the sum into integrals. If we treat the energy classically, then it's just then put to the energy is put to the energy ei psi a equal to ay square, and do the mathematics, you get the relation. Okay, so x square is nothing but a square a x square ay square divided by kt. So if you do the mathematics, you get the 1 by 2 kt is the energy per kinetic energy and potential energy degrees of freedom in the high temperature limit. Okay, so application classical and phase equilibrium. Okay, apply statistical mechanics to develop microscopic models for problems you are treated so far with the macroscopic thermodynamics. If you take the products energy and the reactant energy, so this is for product dissociation energy, reactant dissociation energy. Then the chemical equilibrium. So gas phase, calculate gas Kp from microscopy properties. AA plus BB equal to CVC plus CD DD. Okay. So delta G is nothing but minus RT Kp ln Kp. Kp is nothing but delta G is nothing but product gives free energy minus reactant gives free energy. Okay. For G0 for each species, G is nothing but A plus PV. Then for putting A is nothing but minus KT ln Q, and PV is nothing but NKT. Okay, so then substitute for G, then you know the Q is nothing but Q translational whole power n divided by n factorial into Q interaction whole power n. Okay, so do the mathematics, you get the relation. Okay, so for molecules in the gas phase, the internal degrees of freedom are rotational and vibrational and electronic states. Okay. So interaction is nothing but the rotational, vibrational, and electronic. Okay. So for electronic partition function is nothing but e power d0 divided by kt. Okay. The d0 is the dissociation energy from ground state electronic energy level. Usually no other electronic level matters. Okay. Okay. For q, this is the dissociation energy from the ground state to ground state. So molecule in the ground state, if you take a molecule H2 like that, if you take a molecule H2, it is in the ground state. What is the energy needed to break the bond? Okay, that is the Q electronic. Okay. Okay, Q vibrational equal to summation of all the energy. For 0 ground state and E0, 2 E0, 3 E0, and reduce the formula, you get the answer. Note, we set a 0 of vibrational energy as the lowest vibration energy. The 0 point vibrational energy as we include. So here we note, we include the 0 of vibrational energy as the lowest vibration energy. Here you put the energy 0, but normally the energy not 0. We have the 0 point vibrational energy. So the 0 point vibration energy included in the electronic. Okay, Q electronic. So by using the dissociation energy rather than the bottom of the electronic potential energy. Okay. When KT is at 300 Kelvin, 200 centimeter inverse, most molecular vibrational energy is greater than the 500 centimeters. So most molecules in the ground state. So vibrational is Q partition function equal to 1. Needed to calculate it, but it is not large. Okay. Okay. We have not treated the Q rotational. Okay, because rotational levels are not evenly spaced. Rotational energy has degeneracy J into J plus 1 into E0. Okay. So where J is equal to 0, 1, 2, 3 and E0 equal to 1 centimeter inverse. Okay. At a higher temperature limit, Q rotational is nothing but KT divided by E. So it is approximately 100 to 1000. Okay. So we seen that Q translation 10 power 30 and Q translation divided by N is 10 power 6. So for multiple species in chemical equilibrium, okay, for when there are multiple species, then need to use Ni for each species. Okay, for Ni for each species and use partial pressure values in PV terms. Okay, then you got these relations. Okay. Example, simple reaction at 300 Kelvin. AB plus CD, you break AB and CD, you get form the AC and BD. Okay. Assume all molecules have same vibrational energy frequency. So then Q vibration is equal to 0 for all species. Translational or rotational, high temperature limits. Okay. Assume similar rotational energy depends on moments of energy. Q translational and Q rotational contributes are all equal. Okay. Then the delta G is nothing but minus RT Kp. Kp is nothing but QAC divided by BD divided by QAB and CD. So then substitute for Q AC is nothing but dissociation energy. Okay, E power dissociation energy of AC divided by KT. Like that you substitute. Only the dissociation energy matter, because since the other degrees of freedom contribute equally, they cancel out because the others are equal. So you can cancel out above and below. The only dissociation energy only not cancel out. Okay. So usually energy effects dominate in the chemical equilibrium. Okay, relatively simple case, solid state chemical reaction like A become B, isomerization in an organic molecule crystal, Na molecules of A and Nb molecules of B, then Na plus Nb is equal to N. No translation or rotational, no change in PV. All the changes in the electronic and vibrational energy. Okay. If the vibrational frequencies are the same, then only the difference in dissociation energy is needed. Okay. Okay. So then Q is nothing is only the e power minus EI divided by KT. For a microstate, for energies EI, it is gamma EI e power minus EI divided by KT. Recall entropy due to mixing of two species. So if you do the mathematics, you come to the calculations. Okay. The ground state of all state has n molecules. Okay. For system energy E equal to NB equal to NB delta D0. Probability that the system has the energy is nothing but Na A is Na divided by Q. The average number of P molecule is this relation. Okay, so doing the mathematics, you know. So if vibrational energies differ, then Q vibrational also need to be calculated in general. Low vibrational frequency favor a species since the levels are closely spaced. So there are many low energy states of that species. For chemical reactions involving covalent bonds, the bond energies dominate over entropy. Okay, but the treatment we are given could also be used for much more subtle changes like rotational of CO molecules in a CO crystal. Note the treatment assume no interaction between different unit cell. Okay, this gives rise to a fairly gentle temperature independence of the equilibrium. Okay. Example, if you take a helic coil transition in biopolymers, interaction make fewer longer segments of helix are more stable than the shorter segments, because in the longer segment there are more interaction. So more interaction means energy, less energy means more stable. Okay. So similar for magnetic and non-magnetic domains in a ferromagnetic crystal and in a all sort of. So it is similar for the magnetic and non-magnetic domains in a ferromagnetic crystal and in all sorts of interacting system. Okay. In this case, the temperature difference is not completely abrupt. Okay, but not nearly as gradual as in the non-interacting system. It is not completely abrupt, but not as gradual as non-interacting unit. Extra example using quantum mechanics result for Q translational. Okay, can also calculate solid gas phase equilibria, phase vapor pressure over the crystal. Assume monoatomic ideal gas, only translational partition function. Then the Q translation nothing but Q trans divided by n factorial. So if you do the calculation, you get the answer. Okay. Condition for phase equilibrium is nothing but chemical potential should be same for solid and gas. Okay. So and do the mathematics. Gives vapor pressure of B over crystal, strong binding energy, or low temperature gives low pressure as expected. Low vibrational frequency also gives low pressure since this allows high entropy in the crystal. Okay. So you can calculate the phase diagram, pressure, temperature, phase diagram that you can describe before in the macroscopic terms only. Okay. So I think we go class very much faster. I think some of the terms you should not understand very much. Okay. So if you take time and slowly see these calculation, see these are simple mathematics. Okay, so you can understand better. Okay, thank you. We can elaborately see the topics in the problem solving section because it is like a loop. Okay, so if you first we saw the topic overall, then you do the problem solving, then you can understand the topic better, then you do the problems concept problem. Okay, this is like loop. Okay, so how much you are doing this again and again, you should better understand the concept. If you do the problem, you should understand the concept better, then you should do the process again and again, then only you should understand the concept better and don't need to muck up these mathematics. Okay, so if you know the mathematics, you can simplify as you. There are different ways. There are if you in your mathematics, there are not only one ways. Okay, here you do a one way. You can do other ways also. Okay. Okay. So thank you so much.